Hi, I'm Andy Kane, and I'm going to overview the MTS Axial 809 Axial Torsion machine that we will be using for the torsion lab. Quick overview of all the equipment that we will be using. This is the machine itself, our top and bottom grips. This will be our axial torsional extensometer, and this is a hydraulic pump unit that drives the, movement of this machine. And then lastly, we have our software that controls everything. Let's look at the controls used to drive the axial torsional machine just on this front panel interface. We'll start from the right and work our way left. The first thing we're going to look at is the emergency stop button. If anything goes wrong, you'll probably want to use the software to stop it, but if anything serious is wrong, then you'll push the emergency stop. Next thing is the interlock. The interlock locks and unlocks the crosshead, which is the top beige portion of the machine. When this is locked, it won't allow you to move that, and once it's unlocked, it will allow you to move the crosshead up and down. The next one is the actual crosshead control. This will turn, when you turn it clockwise, it will go up, and when you turn it counterclockwise, it will go down. I can do it now, and nothing happens. That's because the interlock is locked. If I unlock it, I can then move it down and then move it up. And then once you're done, the best practice is to always lock the interlock once you're done moving anything. Working our way over, we've got some controls that you don't need to worry too much about it. They control the speed at which the crosshead and driving actuator is able to move. The next important part is the top grip and bottom grip, whether it's open or closed. Right now it's hard to tell because it is rotated in a way at which doesn't allow you to see the grips, but when I close it, we will rotate using the software to do that. And we'll show you the software here in just a moment. One thing to note is that the only torsion that you can get comes from this bottom driving actuator. The top grip will not rotate at all. It's all the bottom grip. So from the bottom grip, we can close it. It's going to make that noise most of the time. Don't be concerned when you hear that. As you can see at the top and on the sides, that the grip is now closed. The grips we have right now are a cylinder, so that it works good for our torsion samples because we're just using an aluminum cylinder too. And then, you can close the top grip too. You can probably see that up there. And you can open them. But that is your basic controls on the front panel. Also, a thing to note is this remote control. This remote control allows you to control the actuator on the bottom, but we do most of that controls in the software, so you won't have to worry about that in the lab.
Thanks, Andy. My name is Will. I'll be discussing in a little bit more detail about the engineering implications of the MTS machine and also a little bit about why we use it. So, Andy covered the instrument panel, and what I'll be talking to you about is the actual machine itself. So, the MTS machine is very bottom heavy, which is great, and also the side beams are very stiff. So why that's useful is that there's no crosstalk between the machine and actually the instrumentation that's recording data. Why that's important is that you're making sure the data you're recording is actually from the specimen and not from, external moments or loads from the machine itself. The other thing is that the machine is specifically designed with grips that you can replace for square, circular, or different grip teeth to work with different materials. So why that is important is that we actually have these hydraulic grips that are incredibly strong. And the reason for that is to make sure that there's no slippage during the actual torsion testing or axial loading or compression or tension, depending on what kind of test you're doing. what is also dangerous about that is that because they're hydraulic, they can actually crush the material. So in the case of the lab we're doing, they can actually crush the tube. And what we've done is put steel plugs in the hollow tube to make sure that it can't actually crush it. The other thing about the machine is that there's a load cell up here at the top. What's important about that load cell is it's a 100 kilonewton load cell, so it's way too strong, or it has way too high of a capacity for what we're actually measuring in the lab. For example, with the slotted tube, we're only measuring about 40 inch-pound force, and on comparison, 100 kilonewtons is extremely high magnitude as compared to what we're doing with the slotted tube. What is important about that is that we use that for a reference point, and what we actually are using is the Extant, which Trudy will be covering to measure our data during the lab. So you'll see both during the lab, and you'll actually have to work on a little bit why we record both.
Okay. Hello, 3112 students. I'm Trudy Schwartz, and as one of the lab managers here in aerospace, I want to talk to you today about our axial torsional machine and how you get your measurements. One of the first primary measurements you need for this lab is to measure the torque that's being applied to your specimen. So the torque to your specimen is applied by the machine hydraulically through the hydraulic system, and then that is measured by this cylinder up here, which is your axial and torsional load cell. So that measures both axial force, if there's any axial force, but primarily what we care about in this lab is the twisting torque. So that's measured by that load cell, and it has an accuracy of 0.1%, which gives you very good data on that. The next sensor that we need is a sensor to measure the twist angle and the shear angle, the shear strain. So to do that, we have an angle measurement built into the machine that you will get to see in the test. That's an angular displacement transducer. It's located in the bottom of the machine and measures how much this bottom grip is twisting. If you use that as a measurement of phi, you can then calculate gamma, your shear strain. But when you do that, you're going to get the shear strain of everything that is twisting relative to the top, which is not moving. So that is not just the material properties of your steel or aluminum tube, but the properties of the grip and all of the assembly that's in between. That's not the shear modulus that you want, and it could be as much as an order of magnitude off. So you need to measure what the local twist angle and shear strain is. We can do that directly with two different methods. We could use a strain gauge. A strain gauge could be glued onto the specimen, and that strain gauge could be used to measure the shear strain. Or, even simpler and reusable, is to use an extensometer. The extensometer can then be placed on the sample and measure the local shear angle, shear strain, that is measured just in this 1 inch length of the specimen, and give you a very, very accurate measurement of shear modulus G. Okay, could we use strain gauges instead for this measurement? Yes, we could, and we have done that in the past. Strain gauges are nice because they are cheap, but they do take a lot of labor to apply and special glue and soldering them on, and then they can be used. Whereas the extensometer can be used over and over and over again for multiple different types of samples without having to glue anything to that material. The strain gauges themselves are a very small wire that's wound in a pattern. You can look those up online. And the direction of sensitivity is in the lengthwise direction for this strain gauge. So it is measuring strain in the vertical direction at this point. We could choose to put that strain gauge on in different orientations on the material sample. We could have that at 0 degrees, 90 degrees, or 45 degrees. You as the engineer have to decide how that should be applied. So I'm going to reference you to the figure from omega.com. That figure that's being shown, if you look at that figure, has different applications and how you would orient those strain gauges accordingly. So in figure C, you would mount your strain gauges to the top and bottom of your specimen in order to get the tension and compression strain if you were doing bending. We're not doing that in this case, so that doesn't apply to us. You could also look at figure E, In figure E, you would measure shear strain. Notice in figure E that is still with a vertical force on the end of the beam. There would measure the shear strain of the specimen if you apply the gauges at 45 degrees. That still does not apply to our case because that's not how we're loading this specimen. The third one I want to point out quickly is figure D. That one is for axial strain. For axial strain, you could measure the strain that is in line with the applied force, which is axial to the specimen, like you would do in the 1022 dog bone class lab. You could also orient a strain gauge at 90 degrees to get Poisson's strain. The last figure I want to point out is figure F. That one is for torsional strain. So that applies to this lab and what you would do. So if you wanted to measure the torsional strain gamma that's occurring in this rod as it is twisted, you would apply your strain gauges at 45 degrees because that lines up with your principal axes of strain for that loading case. In the extensometer, that's already been done for you. So you don't have to worry about the orientation of the principal axes. In the design of the extensometer, they have determined that in the strain gauges that are inside the extensometer to measure the 45-degree shear strain that's occurring in the torsional application. This extensometer can also measure axial strain, so it also has strain gauges that are oriented to measure any strain that's along the axis of the specimen if you're also pulling the specimen, not just twisting it. So this extensometer can be used for axial strain and torsional strain. We have other extensometers that would need to be used for making other measurements. The other types of extensometers that we have is just a pure axial extensometer. This should look familiar to you from the 1022 class, which measured the axial strain in your dog bone specimen. One extensometer that you have not had a chance to use, but is available for things like senior projects or other research applications or other material testing, is a transverse extensometer. This extensometer can be applied in order to measure Poisson's ratio, so you can get that measurement as well as the axial measurement.
So now that we've covered some of the characteristics of the MTS machine, we're going to talk a little bit more about the hydraulics of it. So because it's a hydraulic machine, it has some advantages and disadvantages. The advantages are that it's very easy to control and it's accurate. It's usually quiet. The machine itself, the pump unit is a different story. But what's nice about it is that you can actually extend the hydraulic power across a large distance. Obviously there's limits to it, but because it's coming from a unit that is actually producing that hydraulic power, you can put it some distance away to the point where you actually can hear it. For our case, it's in the room. We have it off right now, so it's a little bit quieter. But there are some disadvantages as well. Hydraulic fluid can be extremely toxic to the environment that it gets exposed to. It also can be very hot. In our cases, the machine is usually running at 90 degrees C, which you wouldn't want to get on your skin because it would obviously burn you. Other aspects about it that are disadvantages is that it has to be kept very clean. Any particulates that get in it can be extremely damaging to the equipment. You can't see it, but there's a lot of piping under here that is running two different aspects of this machine, and it can be very dangerous. So you're constantly filtering in, and the other aspect of it is that it's very difficult to clean up if there is any spillage. So the way we actually control this machine is through a proportional control system. What we do is we set you into a while loop that basically adjusts the angle of the grip by a certain amount, and then it will check the while loop condition statement, which is have you reached a certain pound force, or I guess torque. Have you reached a certain torque? And then if you haven't, then it will turn it again. And if you have, then it will stop and actually go back. So going into a little bit more detail about the MTS machine's error and what sources of error we can have during the lab, there's 4 different types. There is human error, sample error, sensor error, and software error. For human error, we can have pretty much anything with you or myself interacting with the machine and what it's going to be recording. So that could be incorrect usage of the programming, that could be incorrectly placing the sample inside of the grip, and that could also be, incorrect usage of a certain sample with what programming. So it's a combination of things. There's also sample error. Like I said, you could be using the wrong sample, you could be using the wrong material, and then there also is sensor error. So you could be using the wrong sensor. In our case, we're using an extensometer, but you could also be using a wrong load cell, which is up top. So that load cell can't record the information we need, but it can get close. It doesn't have the correct resolution. And then the last thing is the software error. You could be using the wrong program. The program could be set to record at the wrong rate, and also the software could be incorrectly coded to not go to the correct torque that's desired.